Hello students. Welcome to our Senior Secondary School 2 Physics lesson. Today, we will be learning more about gas laws. A continuation from our previous lesson. But before we proceed, let's quickly recap what we learned in our previous lesson. In our previous lesson, we explored measurements of gas pressure. We defined and explained the fundamental gas laws. And we also explained kinetic molecular theory of gases. Before we begin today's lesson, let's take a quick rundown of our lesson objectives. By the end of today's lesson, you will be able to solve some examples on gas laws and explore the applications of gas laws. Are you ready? Let's get started. Let's solve an example problem addressing Boyle's law. A gas has an initial volume of 4.0 liters, at a pressure of 2.0 atmosphere. If the pressure is increased to 4.0 atmosphere, what is the new volume? Using the formula P1 V1 equals P2 V2. Listing the variables. P1 is equal to 2.0 atmosphere, initial pressure. V1 is equal to 4.0 liters, initial volume. P2 is equal to 4.0 atmosphere, final pressure. V2 equals final volume. Solution. Substitute the given values. P1, which is 2.0 atmosphere times V1, which is 4.0 liters, equals P2, which is 4.0 atmosphere, times V2. Therefore, V2 is equal to 2.0 atmosphere, times 4.0 liters, all over 4.0 atmosphere. Atmosphere cancels out each other. V2 equals 2.0 times 4.0 liters, which gives us 8.0 liters, all over 4.0. 8.0 liters, divided by 4.0 equals 2.0 liters. Therefore the new volume is 2.0 liters. A fixed mass of gas with volume 600 centimeters cubed, at 0 degrees Celsius is heated at constant pressure. Calculate the volume of gas at 130 degrees Celsius. This problem involves Charles's law, which states V1 all over T1 equals V2 all over T2, where V1 is equal to 600 cm cube initial volume. T1 is equal to 0 degrees Celsius, which would be converted to Kelvin. V2 equals final volume. T2 is equal to 130 degrees Celsius, which would also be converted to Kelvin. Solution. First, let's do the conversions. From our previous lesson in heat energy and temperature, we learned that to convert Celsius to Kelvin, we simply add 273. K equals C plus 273. For our first value, 0 degrees Celsius plus 273 Kelvin, that gives us 273 Kelvin. For our second value, 130 degrees Celsius plus 273 Kelvin, that gives us 403 Kelvin. Moving on, we substitute our values into the equation. V1, which is 600 centimeters cubed all over 273 Kelvin, equals V2 all over 403 Kelvin. Now we solve for the initial volume V2. Cross multiply. V2 equals 600 centimeters cubed times 403 Kelvin all over 273 Kelvin. Kelvin cancels each other out. V2 equals 600 times 403 gives us 241,800. Divided by 273, that gives us 886 centimeters cubed. Therefore final volume is 886 centimeters cubed. Note that this figure was approximated. Also have in mind that we convert Celsius to Kelvin because gas laws require absolute temperature for accurate calculations. We convert to Kelvin whenever we are given a value in degrees Celsius. A gas has an initial pressure of 1.5 atmosphere at 200 Kelvin. If the temperature increases to 400 Kelvin, what is the new pressure? Solution. Solving this using the Gay-Lussac's law, which states P1 all over T1 equals P2 all over T2, where P1 is equal to 1.5 atmosphere, initial pressure. T1 is equal to 200 Kelvin initial temperature. P2 equals final pressure. And T2 equals 400 Kelvin final temperature. Substitute the given values. 1.5 atmosphere, which is P1, all over 200 Kelvin, which is T1, equals P2 all over 400 Kelvin, which is T2. Now, solving for P2, we cross multiply. P2 is equal to 1.5 atmosphere times 400 Kelvin all over 200 Kelvin. Kelvin cancels out each other. 1.5 atmosphere times 400 gives us 600 atmosphere, divided by 200. That gives us 3.0 atmosphere. Therefore, final pressure equals 3.0 atmosphere. Well done. It's alright if understanding doesn't happen immediately. Take your time to go over it again. Now let's explore the applications of gas laws in real life. In medicine, gas laws help in respiration. During inhalation, lung volume increases, causing pressure to decrease, drawing air in. During exhalation, lung volume decreases, increasing pressure and pushing air out. Gas law explains how different gases, oxygen, carbon dioxide and nitrogen, contribute to the total pressure in the lungs. Anesthesia. Anesthetic gases dissolve in the bloodstream based on their solubility and partial pressure. Henry's law helps in understanding how gases like nitrous oxide and oxygen mix in the blood. Ventilators and oxygen. Gas laws explain why oxygen is stored in containers and supplied to patients. Oxygen is compressed into high-pressure cylinders to reduce its volume for storage. When released, the gas expands, making it easier to supply to patients. Oxygen is mixed with other gases like nitrogen in ventilators and anesthesia machines to create the correct breathing environment for patients. Blood pressure measurement. A sphygmomanometer, blood pressure meter, uses air pressure to measure blood pressure accurately. Applications of gas laws in engineering. Compressed gas storage. Gases like oxygen, nitrous oxide, and carbon dioxide are stored in high-pressure tanks, expanding when used in medical and industrial applications. Refrigeration and air conditioning. Refrigerants expand and contract based on temperature changes, cooling the surrounding air. Steam power plants. Boilers heat water into steam, expanding gas volume to drive turbines and generate electricity. Rocket propulsion. Expanding gases from burning fuel create thrust, propelling rockets forward. You can go ahead to explore other gas laws. Now it's your turn. Here are 2 quick practice problems. Give them a shot. Remember to pause the screen and solve the problem. Great job so far. Let's recap what we have learned. Gas laws are essential in weather forecasting, medicine, vehicles and gas diffusion. Understanding gas laws is essential for working with gases safely and efficiently. Gas laws ensure that medical oxygen is stored, transported, and administered effectively. In our next lesson, we will be learning about wave motion. You've done amazingly well to complete this session. Remember that knowledge only works when you apply it. See you next time.